In our second lecture, we're going to explore a little bit of the history of astronomy. I'd like to share with you some of the early discoveries and how different cultures were observing the sky and how that gradually led to an improved understanding of the sky, which of course eventually led to our current understanding of the sky. Now I need to emphasize that even the earliest cultures, as they were looking at the sky, were not really doing what you and I would consider science. They were aware of the sky, they noticed various things occurring, but they really weren't exploring it to understand it. They took note of various events, and they used these in various ways. If we have to try to point to one culture that was doing these things at that time, we might point to ancient Babylon. Numerous cultures were aware of the sky and looking at it, but in ancient Babylon, they were very systematic in their observations. They developed constellations, they developed star catalogs, and they began to recognize that many astronomical phenomena were periodic in nature, phases of the moon and sun and so on and so forth. So here we begin to see the earliest observations of the sky, and we'll talk about how they put those to use. Think too of the ancient Egyptian civilization. We know from their writings that they were well aware of the sky and very interested in it. They became very aware of the seasons, and you might recall that they needed to know when the Nile River would flood so as to be able to plant their crops at the right time. You might also recall they're well known for their famous pyramids. They wanted to get these oriented very precisely north and south and east and west. How were they able to do that? Well, again, they were aware of the sky. They knew that there was a particular star in the sky that always pointed north. Today we might call it the North Star, and yet they were able to use it at that time to again orient the pyramids. They were one of the first cultures to divide the day into 24 hours, the year into 365 days, and they did numerous other things as well. Once again, they were quite superstitious in their beliefs about supernatural beings in the sky, gods and goddesses, and yet they were looking at the sky and slowly, gradually learning more about it. Sometime later, in Northern Europe, we know that people were looking at the sky. Perhaps you've heard of the famous Stonehenge. Now Stonehenge, we believe, was an early observatory. Out in the English countryside, there are huge stones placed in circles in such a way that you could stand at the center of these and look out in various directions and watch as different objects might rise or set at various times throughout the year. We think that this enabled that ancient civilization to, again, understand the rising and setting of various bodies and what that might have meant for them. We believe it probably had some, again, superstitious and other supernatural meanings for them, but once again we see here another step forward, thinking in terms of using a location like this to learn more about the sky. In the Far East, the ancient Chinese civilization was busy observing the sky. They developed their own constellations, and they did something that other cultures didn't really do so very much. They became aware of changes in the sky. Now these were pretty rare, but on rare occasions they might notice a new bright star flare up into brightness where there was not one before. Other cultures began to slowly develop an idea that, well, the heavens were perfect and therefore unchanging. Some felt that since that's where the gods lived, surely there was no need for any change. Well, the ancient Chinese did not have such an idea, and when they noticed a new star, they promptly recorded it. Again, these were rare occasions, but very interestingly, we can look back now in their records, notice the location of some of these that they saw, and recognize with today's telescopes that they appeared, or rather they did see, a new star appear where a star exploded and became very, very bright. These today we call supernovae. And so this allows us to track back in time and to realize that at a particular point in time, these were observed by early humans. Even in the Americas, we can tell that the ancient cultures were busy observing the sky as well. We have several examples of that. The Anasazi have shown us that they were well aware of the sky. There's a particular location where a rock formation is such that a thin sliver of sunlight would gradually travel down a rock at a certain day of the year, the first day of summer, and one of them actually drew a number of concentric circles. These concentric circles, when this sliver of light would pierce through them, told them that this was the first day of summer. So kind of an ingenious way to mark that off. In the year 1054, we have evidence that someone saw, again, an exploding star right near the crescent moon. There's actually a painting on the rock face there that we can see. And we're able to go back and realize again from the location that they drew that this was an exploding star, the famous Crab Nebula supernova. So once again, it's interesting to us today to be able to look back and pinpoint that time when they saw that, and we are well aware that these cultures were looking at the sky. So what did they do with this knowledge? Gradually over time, they began to find some practical uses for that. Surely they were able to develop daily, monthly, and annual timekeeping. They began to recognize the need for calendars to know that each year, on certain days, certain events would occur in the sky. These ancient cultures were well aware of the phases of the moon, and again could develop monthly calendars. They watched the planets and stars moving through their motions. Some even were able to predict eclipses, which we'll talk about a little bit later in our course. As far as practical benefits, some would again realize that a good calendar would allow them to know when would be the right time to plant the crops, or when would be the right time to harvest the crops as the seasons moved on throughout the year. Some even began to recognize, again as you mentioned with the Egyptians, that certain stars located at certain positions in the sky would only change their position if you changed your position on Earth. And therefore, if you were a careful observer, you could get a pretty good idea of how far north or south you had moved by carefully looking, for example, at that North Star at the time. So we begin to see, again, the beginnings of astronomy here. Although it wasn't truly a science as we would think of it today, early cultures were definitely looking at the sky, and they were definitely putting that knowledge to use. Now I'd like to switch gears a little bit and talk about a very important culture in many ways, but in our context here of astronomy, that of the ancient Greek civilization. We know for several centuries BC the Greeks rose to prominence in many ways, but we're interested because here we find really the first scientific approach to astronomy. The Greeks looked up at the sky, noticed all the various things going on that others had seen, and they began to ask the question, why? Why is it like that? Why is it doing that? They began to think, what might explain what we see in the sky? Now, interesting, we're going to see in just a few minutes that some of their scholars recognized centuries ago that the Earth was spherical. Contrary to popular belief, not everyone in the ancient world thought the Earth was flat. And so here the Greeks put at the center of their model, so to speak, a spherical Earth. And they then thought, well, it certainly looks as if the stars, the sun, the moon, the planets, all these things are circling around us. And so this was one of the first early models of our solar system and really of the universe. We call that a geocentric or Earth-centered model that the ancient Greeks proposed. But why did I say that we really point to them as the place where a scientific approach began in astronomy? Well, there's three main reasons. Number one, as I mentioned, the Greeks began to move away from explaining what they saw in the sky via the supernatural. Instead of thinking that the reason perhaps Mars is bright tonight is because the god Mars is angry, no, they began to think about other reasons, more natural type reasons. Perhaps Mars is a little closer to us or farther away. So they began to slowly, gradually let go of supernatural explanations and look for natural explanations. And that's what science does today. Number two, as I mentioned, they began to build models to try to explain their observations. Many of them would go out, observe the night sky, come back in, sit down and say, what might explain this? Can we build a model to explain this? And that leads to our third point, is exactly that. They would often reason from their observations. If we see the moon going through these particular phases, perhaps what's going on is that the moon is out in space, the sun is shining on it, and we see it illuminated in various ways at different times. We know too, I'm sure you're aware, that the Greeks were well known for their mathematics, their geometry. They were able to put that to very effective use in the sky, as we're going to see. So, the Greek civilization develops this geocentric model, which frankly would hold sway for many, many centuries, and they begin to move towards the scientific method of learning about the sky. I'd like to share with you one very interesting discovery that was made at that time. I mentioned that some of them were aware that the Earth was spherical. How did they know that? How could you explain that today, if called upon? It certainly looks as if the Earth is flat, doesn't it, when you stand outside? So how do we know that? What is the evidence? Well, I'd like to talk for a minute about a Greek astronomer called Eratosthenes. Eratosthenes developed a very interesting technique to determine the size of the Earth. He understood that the Earth was spherical, and he reasoned that if you stood at one particular location on Earth, for example, the city of Syene, you would see the sun directly overhead on the first day of summer, the summer solstice. You could perhaps hold a stick vertically and it would not throw a shadow. Well, assuming that the Earth was spherical and he wanted to know how big it was, he asked a friend to be in another city, Alexandria, on that same day at exactly the same time, and to hold his stick vertical. And he asked that friend to carefully note the length of the shadow that the stick would throw. Now, the reason for this, as you can see in our diagram, is that obviously a spherical Earth means that the Earth's curvature is having the sun strike it at a different angle. Well, Eratosthenes, based on the measurements, realized that the angle difference here was about 7 degrees, a little bit more than 7 degrees, which he correctly knew was about 1/50th of the full circle around the Earth. And therefore, he realized that the distance around the Earth would be 50 times the distance between the cities. He had asked his friend to pace out the distance between the cities to be very sure of its distance, and when he took that number and multiplied it by 50, he arrived at a figure that was very, very accurate. He measured the size of the Earth to within approximately 1% accuracy using 2 sticks. Quite a remarkable achievement. Very little technology, and yet some careful observations, just a little bit of geometry, told him the size of the Earth. Really an impressive achievement at that time. Well, as time goes on, another very important astronomer appears on the scene. This man's name was Claudius Ptolemy. Ptolemy lived in the late 1st and early 2nd centuries AD, and Ptolemy took all of the knowledge of the ancient world in astronomy and began to compile it. He felt it would be important to collect this knowledge and document it, and obviously that's a good thing, isn't it? And so Ptolemy set about doing this. He ended up writing 13 books, very descriptive, very comprehensive, about all the known astronomy of the time. Stellar motions, solar cycles, lunar phases, constellations. All this was documented in such a way that anyone then would have access to it. Obviously, that would be a very good thing to be able to share with others, to teach them. And really, it became an authoritative summary of astronomy for centuries. Many began to feel, well, Ptolemy has done such a good job at this. Perhaps I don't need to go outside and do a lot of observing. I'll just read his books. And so it was a very, very useful thing that he did there. However, there was one potential downside to that. Over time, as people neglected to go outside and observe, Ptolemy's great work discouraged them from asking questions, exploring, verifying. And so observation declined somewhat, because once again, most anyone would say, well, why don't you just read Ptolemy's books to learn about astronomy. There was one particular problem, though, that needed to be explained, and that was that periodically, if you were a careful observer, you went outside at night over the number of weeks, you would notice the various planets, Mars, Jupiter, Saturn, gradually shifting their position, and yet these three planets occasionally would reverse their direction and go backwards for a short time before resuming their normal motion. This was very difficult to explain because the ancients again believed that these objects circled around the Earth. Why in the world would they stop and go backwards for some time and then begin moving forward? It didn't make sense. Well, Ptolemy had an answer, as you can see here. He invented something called an epicycle. Now, frankly, it's not correct, but it seemed to work pretty good. Ptolemy said that the planet doesn't just move around the Earth on a large circle, but rather the planet moves around a small circle, which then moves around the Earth on the big circle. And as you can see in our diagram here, that would explain why a planet appeared to go backwards occasionally. Well, this only increased the fame and reverence for Ptolemy in explaining such a difficult question of the time. And so all the more so was he regarded as a leading outstanding figure in astronomy. As we'll see shortly, though, the model did not quite perfectly explain the motions of the planets. But for most people at the time, it seemed good enough. Well, as the Greek civilization declines, the Roman civilization then comes onto the scene for several centuries. It eventually declines, and much of Europe goes through a very dark period, sometimes called the Dark Ages. Much science, much learning is pushed to the side, even lost. Well, we can be thankful, though, that there was one civilization that preserved and extended much of what the Greeks had done, and therefore we're able to know about that today. During the 8th to 14th centuries, Islamic scientists took a leading role in astronomy. Not only did they translate ancient Greek documents into Arabic to preserve them, but they did an awful lot of good astronomy themselves. They got quite good at timekeeping, again at navigating by the stars. They developed two instruments, one called a sextant, which would allow them to carefully measure the altitude of stars, and again, be very useful in navigation. They also invented a device called an astrolabe. As you see here, an astrolabe was sort of like a model of the solar system that you could hold in your hands. Various metal discs would be developed and put together in such a way that you could turn those metal discs, and they would show you not only the background stars, but they would show you the position of the moon or the sun or the constellations over time. So it would be a way to literally be able to predict the positions of these over time. So we certainly have a debt to these scholars who preserved that knowledge, refined it, and improved it. By the late 13th, 14th, 15th century, as Europe began to move back out of those dark ages, European scholars then would access their works, these Arabic translations, translate them into Latin, which of course then would eventually lead to various languages of today. And so we see this as a very, very important bridge in astronomy carried forward. As I explained, though, Ptolemy's model of circles upon circles seemed to work pretty good, but not quite perfectly. And some astronomers of the time really wondered about that. They'd try to change the size of the circles. They'd try to fine-tune them a little bit to try to get it better. They could never quite get it just right. In particular, Mars. Mars would often be observed kind of drifting off its expected position just a little bit now and then. Well, as time went on, this became more and more troublesome. And finally, by the mid-1500s, a very important figure stepped forward and proposed an entirely new way to look at our solar system and the universe. This was Nicholas Copernicus. Now, Copernicus understood the climate of the time, that his new proposal might not be accepted very well, so he was somewhat cautious about presenting it, but he wrote a very famous book that explains this new model, essentially a sun-centered, or what we call heliocentric model, where the sun is the center and all the planets, including Earth, now were circling around the sun. This was difficult for many to accept. Earth was regarded as the center of the universe for centuries, since antiquity. Humans were regarded essentially as the center of the universe, and it was very difficult for people to begin to let go of that. It truly was a revolutionary idea that took some time to be accepted. As we moved on even further into the late 1500s, another important figure appeared on the scene when it comes to astronomy. This man's name was Tycho Brahe. Now, Brahe became well known for making very accurate, very systematic, and very good observations of the night sky. Brahe was born into a wealthy family. He was able to approach the King of Denmark and ask for funds to build, essentially, an observatory in which he could conduct these observations. Now, this was still before the invention of the telescope, but Brahe did perhaps the best naked eye observing in history. For 20 years, he would go out and carefully measure the positions of stars and planets and other objects and essentially get what we would today call very good data or measurements on which to try to understand the universe. He developed new instruments that allowed him to do this, and so again we give him credit for kind of pushing forward the, so to speak, technology of the time. What did Brahe find? He found that the existing models, the existing predictions were just plain wrong. Ptolemy's model could not explain the position of objects in the sky, in particular Mars, but others as well. Today scientists would say, well, that indicates that something's wrong with your model. And Brahe knew this. He endeavored to develop his own model. Didn't really work very well either. Wasn't really much of an improvement. He said, well, it sure seems to me the Earth is immobile at the center, and it sure looks like the sun's going around the Earth. Maybe the planets are going around the sun, but the sun's going around the Earth. Well, it really didn't work out that much better and was never truly accepted. As Brahe ages, he realizes he's done a lot of good work. Who's going to make use of it? How could this benefit us? Well, as time goes on, he becomes acquainted with a younger man, very important figure as well in astronomy. And this younger man, Johannes Kepler, is very anxious to not only meet Brahe, but frankly to access all of his observations. Now at first, Brahe's a little bit reluctant, doesn't just want to turn his life's work over to this man, but gradually he begins to see that Kepler is very capable, very competent, and can make good use of his observations. So he gradually allows Kepler access to his work. Kepler is not so much known for his observational skills as really his mathematical skills. And as a result, when he sees Brahe's observations, he tries and tries and tries to develop a model that will explain these. And at some point, he's faced with a dilemma. Either Kepler abides by the knowledge and understanding and model that's held sway for centuries, or he realizes it's time for a complete break, that he's going to have to come up with a new model, perhaps this new sun-centered model. In his observations, Brahe had done a good job, and Kepler trusted his observations. He was willing to let go of the prevailing belief and have confidence that Brahe had done an excellent job and that a new understanding of the universe should be based on Brahe's observations. I keep mentioning Mars as being the object that seemed to be off track the most, and sure enough, Kepler finally realizes that Mars' orbit cannot be explained by a perfect circle. It simply won't work. So he instead fits an ellipse to Mars, or an elliptical orbit, and suddenly it makes sense. Now that might not seem all that important to you and I today, but it was really a breakthrough because it enabled him to discover 3 laws of planetary motion. We're going to take a look at those now. So Johannes Kepler really becomes known as the father of celestial mechanics. Here you see the first law, and very simply, it's that an orbit of a planet around the sun is an ellipse. Therefore, the planet gets closer to the sun on occasion and farther from the sun on occasion. We call that the perihelion and aphelion. Kepler then realizes there's a second law of motion, and that is as the planet moves around its orbit, it sweeps out equal areas in equal times. What does that mean? Well, if you look at our diagram here, you'll see that the planet, when closer to the sun, is moving faster and therefore covers a greater distance in the same amount of time that it would cover at a greater distance when it's traveling slower. So how could we maybe rephrase that? What does that really mean? Simply put, planets travel faster when nearer the sun and slower when farther. This is what explained the discrepancy in Mars' positions. There were times when Mars, with an elliptical orbit, was closer to the sun, moved a little bit faster, a little bit ahead of schedule. There were other times when Mars was a little farther from the sun, moved a little slower, kind of fell behind schedule just a little bit. This was a breakthrough in understanding the motions of the planets. Finally, Kepler comes to understand a third law. It's a mathematical law, as you can see here. P squared equals 8 to the third. Now again, I promised you wouldn't have to worry about the math. What does this really mean? It simply means that the period, or the amount of time that the planet requires to orbit the sun, is related to its distance. In this case, its average distance. And therefore, if we know one piece of information, we can easily determine the other. To this day, if astronomers wish to determine the distance to some object that's discovered, they will carefully measure its motion and come up with a number that tells them how long it takes to travel around the sun. This then will directly tell them the distance to the object. So a very powerful tool here for exploring our solar system. So this is where matter stood as the 1500s began to change into the 1600s. Kepler had discovered these laws based on Brahe's observations. Although most people had not yet accepted Copernicus' sun-centered model, it was slowly becoming apparent that this had to be the case. Well, this is the point in time in which another very important figure appears on the scene. You're probably familiar with the name Galileo. Now, Galileo was an Italian scholar, and frankly, he did not invent the telescope. He did hear about it, and yet Galileo receives credit for really being the first one to use the telescope to observe the heavens. And so in the fall of 1609, as he takes this telescope out and looks up to the sky, Galileo sees things no one's ever seen before. What a remarkable time that must have been. He sees craters on the moon. As we'll see in just a second, he sees things with Venus and Jupiter, even the sun he looks at. He's very excited, of course. He wants to share what he's seen. He invites various ones to come look for themselves. And yet the intellectual and even the religious climate of the time means that many people are very skeptical. They're not quite ready to accept things that go against their beliefs. In fact, you might know that at the time even the Catholic Church forced him to recant some of his beliefs. But the point for us today is that Galileo knew what he saw. The undeniable evidence was there for anyone who would look with an open mind. And here's really the point. His observations proved Copernicus' sun-centered model was correct. So here was the evidence now. Here was the proof, so to speak, to finally put to rest the old Earth-centered model of the universe. So again, as he looked up, first of all, people had assumed the heavens were perfect. Surely every object in the heavens was perfect. That implied no imperfections. When Galileo looked at the moon and saw craters, some viewed that as imperfections. Galileo said, well, have a look for yourself. The moon isn't perfectly smooth, but it does have some imperfections. When Galileo turned his telescope to Jupiter, he was entranced to see the planet surrounded by 4 tiny little objects that looked like stars. Today we know they were moons orbiting around Jupiter. Why was that significant? Well, you'll recall that in the old model of Ptolemy, the Earth-centered model, everything circled the Earth. Well, this was a clear contradiction of that here we see objects circling around Jupiter. So clearly, Ptolemy's model could not be right. Even further, when Galileo turned his telescope to Venus, he saw something very interesting. He saw Venus appear to change its phase, very much like our moon goes through phases, from crescent moon to quarter moon to gibbous moon to full moon. Why was that so significant? Well, if you look closely at our diagram here, you'll see on the left that in the old Earth-centered Ptolemaic view, this wasn't possible. This simply wasn't possible. You would never see Venus appear fully illuminated or nearly fully illuminated. It simply wouldn't happen. On the right side, though, the correct model with the sun at the center and Earth farther from the sun, it becomes immediately apparent that yes, as Venus circles the sun, it's going to pull ahead of Earth at some point, and we're going to watch it appear to change phases. Simply put, this was undeniable proof that both the Earth and Venus circled the sun. So this was really ultimately kind of the final blow to that Earth-centered universe. This really did prove that Earth was a planet circling the sun. These days, of course, we recognize that simple fact, and we realize that what we see is a reflection of where we are. We're, in a sense, on a moving platform, so to speak, as we view Venus and Jupiter and other objects. We have to keep that in mind. Planets may appear near the sun, they may appear far from the sun, but the point is much of that is due to our motion as well. Well, finally, I'd like to wrap up by touching on one more historical giant, so to speak. You're probably familiar with the name Isaac Newton. Isaac Newton comes along in the late 1600s. He's well aware of what's come before him, the advances of Copernicus, Kepler, Galileo. But these earlier scientists had not quite been able to explain why things happened in the sky. They really were only able to describe what was happening in the sky. Well, Newton is determined and fascinated to try to explain that. Through his work, his experiments, he discovers 3 laws of motion that we use today, and he realizes that heavenly bodies can affect one another. Okay? This, of course, the law of gravitation. We know that Newton realized that the moon traveled around the Earth because of gravitation. You can see our diagram here. Simple explanation of gravity. We see 2 large masses, perhaps 2 planets or moons or whatever they may be. There is a natural attractive force between them. That force, the strength of that force, is based on 2 main things. Number 1, the masses of those objects, and number 2, their distances. So some of you can appreciate that equation there. But for our discussion, again, the point really is Newton went beyond describing what the heavenly bodies were doing. Finally, here for the first time, we had our first good explanation of why they did it. Simply put, because of these laws of motion that held not only on Earth, but in the heavens, and because of this law of gravity. So I think you've seen in this brief review some of the history of astronomy, how far we came over these centuries. And by the time of Newton, humans were poised now. They were equipped with certain concepts that would allow us to go much, much further, as we're going to see in future lectures. So let's do a quick summary then of what we discussed. We started out by looking at some ancient societies. They had advances in observing the sky, and they put those to good use by looking at those heavenly bodies, developing timekeeping, navigation. Some even began to build simple structures to help them track the motions in the sky. We spent a few minutes talking about the ancient Greek civilization, how they began what we would today call scientific astronomy. They began to do important things such as developing models based on their observations, looking for natural explanations rather than supernatural, and finally using mathematics and reasoning to improve their models. Of course, they developed this Earth-centered or geocentric model. Ptolemy was a major figure there, but even though he was able to explain the motions relatively well, it was never quite perfect. And eventually, centuries later, it had to be replaced. We saw then Copernicus proposing a sun-centered model. We saw Brahe providing the observations, Kepler taking those observations and discovering planetary laws of motion that we still use today. Finally, Galileo. His telescopic observations provided the evidence, the proof really, to tell us that it was a sun-centered solar system. And ultimately, Newton then discovered laws of motion and the law of gravity, which helped explain not only what the planets were doing, but why they were doing it. So I hope you've enjoyed our little review of ancient astronomy, and we'll pick up next time with our next lecture.